In this last segment, we're going to touch on two small additions to stoichiometry. One is going to be percent yield, and the other one is going to be limiting reactance. I'm going to have you read up on both, but we're going to focus on percent yield in this first week. I put a quote here. It's from a Rolling Stones song. You can't always get what you want. And if you look, that's also hyperlinked. So if you want to watch the video and listen to the song, you can listen to it. But the idea here is that rarely do chemical reactions in a lab go perfectly. Oftentimes, what we calculate isn't what we find we get in the lab. There's a variety of reasons for that. It doesn't mean you did anything wrong. Oftentimes, there are other dynamics outside of our control that limit how far a reaction can go. Reactions rarely go to 100%, and so when you calculate what you should get, you end up coming up short. And so oftentimes in industry, we have to aim just a little bit higher. That's where knowing these percent yields can come in handy. So what you're looking for here is that percent. Now, a couple things to keep in mind. Percent yield implies that we're solving for a product. So I want you to keep that in the back of your mind as we go through here. Everything that you're calculating in stoichiometry is only theoretical. It's not until your feet hit the ground that you are doing the experiment that you'll actually find out what you get. Percent yield is just like any other percent problem. It's a part over a whole times 100. In this case, the part is what you got. When you went in the lab, what did you get? In theory, what did you calculate you should have gotten? And again, your actual will always be less than your theoretical, or your theoretical will always be more than your actual if you did everything correctly. So if you measured everything correctly and you didn't make any human errors in the lab, this is what you'll find to be true. First example I'm going to take is on page 23, number 2A. This is hypothetical. It doesn't involve any real chemical compounds. It's just dealing with a hypothetical balanced equation where we are only concerned with mole values. So in this one, I want to find the percent yield. If I take 0.0251 moles of A, that's a reactant, and I actually get in the lab 0.0349 moles of C. Now, this isn't what I would expect if I go through and calculate this. So 0.0349 moles of C, C is a product, that's my actual yield. That's what I got. What I want to do is figure out what should I have gotten. So what you want to do is calculate the theoretical yield first. And this just comes from stoichiometry. If you look at the mole map in detail, we're already at mole of known, and we are going to calculate mole of unknown. So it's a simple one-step problem. If you take a look when I set this up, I immediately go into a fraction that is mole over mole. So those numbers come from the coefficients in the balanced equation. So when I multiply that, it's essentially multiplying by 2. I get 0.0502 moles of C in theory, okay? When I did the lab, I got less than that. So the theoretical is more than what I got. That makes sense. So I've got a theoretical and an actual. Now I can go in and I can calculate the percent yield. So I take that actual yield that I got over the theoretical yield that I thought I should have gotten, and then I multiply that by 100 to make a percent. So in this reaction, that's only a 69.5% yield. So if I wanted to produce a certain amount of product, I'd have to aim roughly 30% higher. in order to get what I need. Now, that's a hypothetical. Let's take a look at a more concrete one. Page 24, number 5, letter B. In this reaction, we're reacting carbon disulfide with chlorine gas to produce two products, carbon tetrachloride and disulfur dichloride. What I'm concerned about is if I start with 67.5 grams of the reactant chlorine and I produce 39.5 grams of disulfur dichloride, what's my percent yield? Now, that 39.5 grams of disulfur dichloride is what I got. That is an actual yield. What I want to do is find the theoretical yield, and that should be more than 39.5 if I do it correctly. So I set up the equation. Now, in this case, I'm starting at mass of known, and I'm going to mass of unknown. When I calculate percent yield, the theoretical and actual have to be in the same unit. So my actual is given in mass, so my theoretical has to be calculated in mass. So I go from mass of known to mole of known to mole of unknown, and then mole of unknown to mass of unknown. That's my setup. Now, when I calculate that, I get 42.9 grams of disulfur dichloride, and that's more than what I got. So my theoretical is more than what I actually got, which should happen. So then I simply plug those in, and I find out that I get a 92.1% yield. Now, in this case, I went through this pretty fast. Here's what I want you guys to do. I'm going to assign you a very small problem set. It is a short week. So what I've got for you is pages 15 through 17, but I want you to skip problem numbers 11, 12, and 13. Those deal with limiting reactants. I only want to focus on the percent yield math problems, but I do want you to read up on limiting reactants and complete those fill-in-the-blank problems as well. I'll have the answers to these posted on the website so you can check those. And then we can talk more on Wednesday if you have questions. I'll have a shorter and more condensed version of an assessment in Skyward that'll be available at noon on Wednesday. Good luck, and I hope to hear some questions from you on Wednesday.